Allora no, io parto. Ok, so let me start from the discussion we had last lecture, and I want to complete our analysis about adiabatic evolution. Okay, so let me summarize, because I think that there are a few steps which are not as easy as I thought, and if you did it, then very good, but we should discuss about this. So I would like to analyze a situation in which I have a time-dependent Hamiltonian, okay, h of t, and let's put it in this way. So there is for simplicity, some time scales, which I call capital T, which characterize the time evolution of the Hamiltonian. So the speed that, I mean, the inverse speed at which this Hamiltonian changes with time. Now, I would like to analyze the regime of parameters in which this time scale is much larger than some internal time scales of the system. Okay, let's call it natural. The natural time scale of the system. Okay, in the picture of the pendulum that we saw last time, then suppose that you have a pendulum and you just change the length of the pendulum. This pendulum can be classical, quantum mechanically, whatever. Okay. Now, the pendulum will have its own natural frequency. In the case of pendulum, it's very simple. It's just it's related to the frequency of oscillations. Let's consider an harmonic pendulum for simplicity. And so I really would like to consider the case in which the time scale of variation of the Hamiltonian is much larger than the period of the pendulum. Okay, but the discussion, as we saw last time, applies in general. Now, this regime is called adiabatic regime. In the general situation, we saw that we can talk about the adiabatic regime when this capital T is much larger than h bar over the energy difference between the eigenstates. Okay, the instantaneous eigenstate of the Hamiltonian. So I just remind you what we found last time. So we just said, okay, let's use a representation of the time evolution of the state in the form of sum over n of Cn of t e to the minus I integral of En of t prime dt prime times, I call it, did I call phi n of t? Can you confirm? Because I call it phi n of t, right? And where we introduce this instantaneous eigenstate, which are defined like phi n, sorry, phi n of t e n of t. So So these are the instantaneous eigenstate and eigenfunction. I remind you, this equation is something which is convenient for us, but there is no concept of in reality of an instantaneous eigenstate. Okay, so because this equation is a way to formulate a convenient basis for us. Is not this equation, I really stress it several times, this equation does not represent any physical evolution, okay? Because you know that if you have time-dependent problems, then you have to solve the time-dependent Schrödinger equation, okay? But it turns out that this is very convenient. Why it is very convenient? Because it is possible to write down, so using this representation, the equation that Cn of t should obey, which is Cn of t is equal to minus, Cm of t, m of t scalar product with m dot of t minus sum over n different from m of Cn of t. I'm just repeating what I said last time. So En, this is En of t minus Em of t, and then I have an exponential of minus the integral over dt prime of the difference En of t minus En of t prime minus En of t prime. Okay, this is what we got, and here I forgot, I just write it here, Cm of t. Okay, now did you try to derive this equation? You can say yes or no.
Yes, but I didn't get it.
Okay, I think that so let's see if, because there is a tricky step that I need to explain you. So that is the following. Now, so the first step to derive it is just to start from the Schrödinger equation that I write here. So it's I dt of psi of t equal h of t psi of t, right? So what we do is just taking this equation, take the derivative, and then we get several terms. Okay, we wrote explicitly last time, and then we multiply the Schrödinger equation expressed in this form to the left with the bra phi m of t. Okay, so just multiplying by this, then we get some expression, and that there is some trick that you need to find out. That is the following. So first of all, so we said that you use this decomposition here with the time derivative, and you substitute, and then we just you just multiply with phi m of t. Okay, left left hand side and right hand side. So once you do this, you just get an equation from Cm dot. Are you with me up to here?
Yes.
I just said I heard one yes. I would like to hear if there are no.
Yes, yes.
2,
Yes.
3. Sooner or later, I will force
Yes.
to speak. 4. 4 out of 9.
Yes, yes.
Yes.
Okay, there were 2 yes, but from the same person. So this counts for 1. Okay, so we are up
Yes.
to 6.
Yes.
Very good. And the other 3, the rest are there.
Yes.
Oh, so okay, you can forget. I should tell you that you can cheat me, because sometimes I cannot distinguish between the different voices. So if the same person use the same changed voices, then you can fool me. Okay. Now, I think that the difficult part where you got stuck was the following. I remind you that we made the assumption that the spectrum is always non-degenerate. Okay. And the reason is that you see that here there are this denominator, so we don't want that there are levels which are degenerate in any point of the spectrum. If the level become degenerate, the derivation and whole discussion change completely. So it's a different story. Okay. I think you end up with something which was something difficult related to this point, that you had this type of terms. You had to deal with this type of terms, right? And then you see that on the other side, instead of having these terms, you get this thing here. So let's see. So the first thing you have to do is to distinguish the case in which m is equal to n, and you get this term here, which is separate. And then you have also m different from n. So the 2 instantaneous eigenstate belong to 2 different eigen energies. Okay. So let me consider only m different from n. Okay. Now, in order to get expression of m scalar dot, the scalar product with n dot, the thing you, oh, sorry. You should have stopped me, because I made a little mess. Should I correct it? These are phi. Okay. So these are phi m, phi m, phi m, phi n, and this dot. Okay. Phi m, phi dot n. Okay. I was calling with a different notation, but it's phi m, not m. Okay. Now you have to compute this thing here. Now, well, actually, how to transform this in something which is phi m h dot phi n over E n minus E m. So what you have to do is just to take the derivative of this, of the, so just take the derivative of the instantaneous Schrödinger equation. So you have h dot phi n of t plus h phi dot of n is equal to a dot n phi n minus, sorry, plus E n En phi dot n. Okay, so if you multiply with phi m both sides, then you get phi m h dot phi n plus E m phi dot n, because h applied to phi n is just phi, this is phi m, equal E dot n phi m phi n, which is 0 because these are orthogonal, plus En phi m phi dot n. Okay, if you put things together, then you find out from here you get the phi m phi dot n is equal to phi m h dot phi n divided by En minus Em. Okay, is it okay now? How to get this term? Hello?
Yes, for me.
Okay. Now, why it is important to write it in this form? Because when you write, so if you have such a term phi m phi dot n, you don't know really what is the weight of this in the dynamics. But in this form here, then you see that when the matrix element on the numerator is much smaller than the denominator, okay, so look, I just want to write it in this form. I want to write it in a phi dot phi m n divided by h bar. So let me be okay. So you see that h bar over En minus Em is a time scale. So each energy difference between two levels fixes a kind of time scale. So just take the smallest gap, the smallest possible difference between En and M fixes the largest natural time of the system you are considering. Now you see that if you have the matrix element which is much smaller, so if the time scales associated to this evolution is sorry, there is something, just a moment. Sorry, there is so okay, so let me say, because there is something not good. Let me be more precise. So let's say this, so because this expression is for so Hamiltonian divided by time, and here I have energies, so I have to just write it in a in a proper way. So actually, this is not a good explanation. Let me do it differently. So let me do it differently. So if you have this, and I just put again the h bar. So I have to write this object like h bar over, I want to consider this phi m h dot phi n over, I take the square, just to have something which is dimensionless, okay? If this is, or actually it should be the sum, but let's consider for simplicity, if this is much smaller than 1, then what happened is that, sorry, this is not there. Then you see that you have that the time scale, now I can write it in this way, in a nicer way, em minus en modulus times, and here I have h bar phi m h dot phi n divided by en minus em. Now you see that this is a time, the time I told you. This is also a time. So if the matrix elements are such that they are at the time scale of the evolution of the Hamiltonian is much slower than h bar over the minimum gap, then you can forget about this term here. Okay, so you can forget about this term here over the previous one, this here. So you just drop it, and then what means is that
Sorry, Professor.
yes.
I think I don't get that second line, the second last line.
Yeah.
Yes, yeah, where you have put it much less than 1. I don't see how.
So it's not that I'm just saying, let's consider the case in which this is much less than 1. So if the Hamiltonian is very slowly varying, h dot will go to 0. Okay, because if it's constant, then this is exactly 0, right?
Sorry, Professor.
Yes.
I didn't get why did you multiply by h bar?
Yes,
and
I explain you. So let's look at this equation, okay? Now, this equation, what is the dimension of Cm dot? Just tell me, what is the dimension of the physical dimension of C dot M? Hello? Just try, don't worry. I mean, even if you say something wrong, don't worry. It's better that you just try it.
I don't know, it's coefficient which depends on
well, okay,
time.
let's start. What is the dimension, the physical dimension of Cm? There is no, it's adimensional, right? Because it's a coefficient of the wave function.
Yeah.
Okay, so what is the dimension of C dot M?
1 over t.
Very good. So it's 1 over time. Okay, so you see that this is the dimension of this is 1 over time. Okay, so I just point it here. This is 1 over time. This is 1 over time because it's a scalar product of phi dot. Okay, so phi dot is 1 over time, right?
Yes.
Now you see that this second term, this term here is dimension 1 over time. Okay? Okay? Because you see, let's say, I'll show you it here different. So we have phi h dot phi over E n minus E m. Okay? So this is energy over time, and this is energy. Okay? And this is 1 over time, right? Okay? So I go back to the previous slides. Now, if I want to decide when this term is much smaller than this, then I better consider dimensionless quantities. Okay? So I cannot say that some dimension full quantity is much smaller. I mean, I can compare just dimensionless quantity and decide when they are small and or large. You agree with this?
Yes.
Okay. So then I ask another question to you. So if I ask you, what is the time scale over Cn change in time? The time scale, you see each component phi n changes with the on a scale which is given by En, right? Or actually h bar over En, okay? So what I want to say is the following. Just imagine that you have only two components. So I have C1, let's consider this for time independent. So I have E1t, phi 1, plus, so this is my psi of t, okay? I'm considering this simple example. And I have minus E2 of t, phi 2, okay? If I ask you, what is the time scale over which the wave function, the coefficient change in time? Well, you can see that I can just put E1 in multiplying everything, and I have C1 phi 1 plus C2 e to the minus, so this 2, E1 minus E2 times t, phi 2, right? So this is a global phase, does not matter. Global phases do not play any role. So if you see the typical time scale of changing of the Hamiltonian, in this case, is just h bar over E1 minus E2. Okay, I just put here, I should put h bar if I want to do it correctly with units. Okay. So the time scale of changes of the coefficients is of the order of h bar over E1 minus E2, if I have only two levels, right?
Yes.
Okay. So if I have many levels, I do not have a symbol, just E1 minus E2, but I have to consider all possible gaps, all possible energy differences. And so I have to compare this time scale with h bar over, okay. So I have to, oops, sorry, I just made a mess. Okay. So I have to compare this thing, this time here, which is the natural time, with the time which comes from this equation. Okay, so since the first term changes over a scale of h bar over the energy difference, I want to see when the second term changes, the changes of the second term are much smaller over the first one. Okay.
Yes.
Look, if it's not okay, I'm happy to repeat
it's okay.
it. You should say, don't be shy, okay?
No, but I have a question. If we want to compare, why we multiply? I mean, it's better to divide and see if it is, and compare it with one. Did you get my question?
So can you repeat? I did not understand the question.
Okay, you said we want to compare the time scale with the other one.
Yeah.
But here you multiply the two terms.
Oh, because yeah. So you see that this as dimension time, this as dimension 1 over time.
Oh, I see.
So it's like, I mean, I have to divide, but I divided the T1 divided by T2, but okay.
I see. To get something dimensionless.
To get something dimensionless, okay. So once I get something dimensionless, then I can check when the second term, when this term can be disregarded with respect to the first one. Okay. Now, essentially, when this comparison of time is much smaller than 1, then I can drop the second term. Okay.
Yes.
So when but then there is a very important simplification to that.
Professor?
Yes.
There is a message in the chat.
Oh, thank you. Sorry, I was looking at notes. Yeah. Oh, do you hear me now? So can you tell me if it's, because the question was, suddenly I cannot hear you, but do everybody else hear me?
Yes, from here.
Clearly.
Okay, so just a moment, just the end. Okay. So please talk. Just say whatever so that we check if the end is hearing. Okay. So Balien is not. Do you have a way to contact the end?
Well,
I
can
think
try.
she's. Oh, Wi-Fi lost. What can we do?
I think now she can hear you, but she cannot speak.
Okay. So, but just a moment. Okay. So, Lien, so if you have question, you just write on the board, now on the chat. Now, what I was just a moment. Yes. Now, when this is much smaller than 1, This is much smaller than 1 when the dynamics, when the changes in the Hamiltonian are much slower than the typical time scale. This is the adiabatic regime. Now, what is special about the adiabatic regime? In the adiabatic regime, what we had before for the equation for m, I keep writing m, phi m, phi dot m equals cm. So the equation, they become uncoupled for any coefficient cm. Okay, so you see that this is very important. Just I really would like that you appreciate this. This equation here, in this equation, all the coefficients cm, they form a system of equations, with a system of coupled equations that you have to solve all together. Okay, but in the adiabatic regime, then the coupling disappears in first order. I mean, this is, then there are corrections, of course, but in the first order, the coupling between the different coefficients disappears. This means the following. This means that, okay, the solution to this equation is very simple. So you just get Cm of t is equal to e to the minus the integral over dt prime, and this phi dot Cm of 0. Okay, this is the solution. Now, what does it mean? It means that the true evolution of the state in the adiabatic regime, let's call it psi of t. I just put almost because it's not an exact solution, but it is something. Oh, there is a question. No, I know. It is something which is getting better and better the slower is the Hamiltonian. The solution is something like e to the minus integral of dt prime phi dot times e to the minus I integral of e. Sorry, I forgot to write something. Sum over m over e m of t prime. So I should put here m c m of 0 phi m of t. This is the integral between 0 and t. Okay. So I remind you that phi m of t are the instantaneous eigenstate. So what does it mean, this? It means that, let's consider a specific example. Let's suppose that Cm of 0 is just delta m k. Okay, so you just prepare the system in a given eigenstate of the Hamiltonian h of 0 in the state k. If this is the case, then psi of t is just equal to e to the minus this, I don't write it, okay, phi k of t. So what does it mean, this expression? It means that in the adiabatic regime, if you prepare the system in a given eigenstate, and then you change the Hamiltonian very slowly, the Hamiltonian will remain in the instantaneous eigenstate. And it will remain in the instantaneous eigenstate up to a phase which has two components. One component which is just related to the integral of Em of t dt prime. This is called dynamical phase. And then there is this second term. So this is dynamical. This is a new term, which actually people knew that it was there, but nobody gave any physical meaning to that until the time in which there was a paper by Michael Berry in, let me check, I think it was in the 80s, but I don't remember exactly, in 84.
Sorry.
Yes?
Can you please repeat the explanation from CM0 when you define CM0 as delta MK?
Yeah. So what I would like to do is to understand. So up to here is okay, right?
Yeah.
Okay. So we found out that when the Hamiltonian changes over time scales, which are very slow as compared to the inverse gaps. I mean, the h bar over the difference between the energy differences, then this decoupled. Okay, so we get that each Cm using the basis of the instantaneous eigenstate then can be solved by itself. And it's just each Cm acquires a phase. Do you remember last lecture I told you that this term is pure imaginary? Okay, so this is just a phase. This will look like e to the I phi g of t. Okay, it's like when you can compute this integral, it's just a purely imaginary. Okay, and this is important because if it was not pure imaginary, then this meant that normalization is not preserved. So now, what does it really mean that each coefficient evolves by itself in the basis of the instantaneous eigenstate? So to do this, I consider the simplest case in which the system is initially prepared in an eigenstate of H0. So I suppose that psi at time equals 0 is equal to phi k of 0, where phi k of 0 is nothing else than h of 0 phi k of 0 equal e k of 0 phi k of 0. Okay, so this is the instantaneous solution of the Schrödinger equation at the initial time, and I prepare the psi in this particular state, phi k of 0. Okay, then if I prepare this, I would like to know how it evolves in time. Oh, sorry, how it evolves. How it evolves in time. Okay, so do you agree that if this is the preparation in our language, it means that Cm of 0 is just del time of k? Okay.
Yeah.
Okay. So this means that if I substitute this here, then it turns out that psi of t is nothing else than just phi k of t times some phase factors. Okay. So what does it mean? It means that actually in the case in which the dynamics is very slow, then the wave function is such that if you prepare in a given eigenstate, the system will remain in the instantaneous eigenstate. Is it better now or?
Oh yeah.
Okay. Now, so in this picture of the pendulum, it means that if you pull the rope very slow of your quantum pendulum, then the system, if you prepare in the ground state, it will remain in the ground state, but it is the ground state of the shorter pendulum. Okay, so it's not the ground state of the, it's not the initial ground state. So for instance, the energy of the system, if you pull it very slowly and you change the frequency of the system from omega 0 to omega 1, initially it had an energy of h bar omega 0 in the ground state. Then after a while, the energy has changed and it will be h bar of omega 1. So it will be the ground state of the new Hamiltonian. Is it clear now?
Yes.
Okay, very good. So this is important. But so for the energy and for the state, then what we found, what we find is that in the adiabatic approximation, the state is just the instantaneous eigenstate. However, there are phase factors that are acquired. Now, the phase factor have a double origin. This is just the phase which is accumulating in time. This one. Okay, it's like e to the minus I energy times the time. And then there is this weird term. This weird term, as I said, was always ignored up to the point in which there was a very important paper by Berry in the 80s that found out that this phase, which now carries name Berry phase, has has some physics. And this is a geometric phase, and you will see under which condition. I mean, there are also generalization, but I will introduce the idea in the context of Berry's first paper. So let me add the following. In this case, so in the case in which you start from in a given eigenstate, then of course these are global phases. So both are global phases and will not play any role. So you may say, okay, but why should I bother? Well, just imagine the following, that psi of 0 is prepared in two eigenstates. So it's prepared in the state 1 over square root of 2 phi k of 0 plus phi L of 0. Okay, this is the initial state when, well, let's use this the same property. sorry, the same rule in the adiabatic limit, psi of t will be equal to 1 over square root of 2. And sorry, I'm pedantic here, but just to show you what I mean. Then, oh, sorry, what does it mean here for the coefficient Cm of 0 is nothing else than 1 over square root of 2 delta mk plus delta ml. Okay, so I just substitute and then I get e to the minus the integral over phi k phi dot k times e to the minus I integral over ek phi k of t plus 1 over square root of 2 e to the minus the integral of phi l phi dot l times e to the minus I el phi l of t. Okay, now you see that once you have a superposition, then these phase factors will matter. And since this is a superposition of two initial eigenstates, the phases that will appear have different meaning, sorry, different values, so they may lead to some interference phenomena. Okay, are you with me, or can I proceed further?
Sorry.
Yes.
K and L are two states.
Two eigenstates of the initial
eigenstates.
Hamiltonian. Yes.
Yeah, just I want to verify.
Okay. I mean, I would like to hear about the others. Is it okay, or should I? So can I go on or stop? Not stop. I mean, should I? Can I continue, or do you need to clarify some parts of it? Hello? Hello? Do you hear me?
Yes.
So is it okay, or can I continue?
Yes, you can continue, Professor.
Okay, I would like to hear from the others.
You can continue.
Okay. Now, I would like to discuss the weird properties of this phase here, which, as I said, has been named Berry phase. So you can get, I mean, you will get notes from for the course of quantum mechanics. Did Giuseppe Santoro send you the notes or not? Or what we did? Hello?
Yes, he sent us the note.
Of the whole course, also this part.
Yeah, of the world course, but I don't think there is a talk on Barry phases.
No, there is none. So that's
Yes.
why I'm saying. So for Berry phase, then you have to go to the library, get this paper by M.V. Berry, Proceedings of the Royal Society of London, It's volume 392, page 45, and the year is 84. Now, the notation that I used in the first part is something that you can find in this paper, but you should read only the first 1.5 pages. Don't worry. I mean, you just look at from equation 1 to equation 6. Okay. The rest is complicated from equation 1 to equation 6 of this paper. Physical review letters, and the volume is volume 58, page is 1593, and the year is 1987. Okay, so you can find all this in the library. If you have problems, write me, and I will find it. Okay, I will get this.
Okay.
Okay, so let's go back to to this problem. So we have this term here, integral between 0 and t of tt prime phi n of t prime phi dot m of t prime. Okay, so now I want to consider the following. I want to consider, so far I just discussed the general case in which there is a slow time dependence. Now I would like to specify to the case in which this time dependence is related to the fact that certain parameters of the Hamiltonian change in time. Okay, just imagine, so you have a spin in a magnetic field, and just imagine that what you change in time is because, for instance, the magnetic field is rotating very slowly. Okay, so that the dependence on, so the time dependence is just through the dependence of this Hamiltonian. Okay, now suppose now I would like to consider the case in which there is a cyclic change of the parameters. Okay, R means the following. So in the picture, I suppose that you start with a given magnetic field. You just do very good. So you already found the paper. Excellent. So I want to consider a case in which you just start from a given situation. So you have a state here. You do something, and you end up with the initial state of the parameters. So that after a time t, these parameters go back to the initial value. Okay, so this means that if this is the case, then the state up to a time t will become similar to the initial. So suppose that it started from phi of k, will go back to phi of k, but then you get something like the integral between 0 and capital T of dt prime of phi k phi dot k, and then you have e to the minus the integral, okay, the ek of t prime. So now, if you let's look at this phase here. So Berry showed that actually this phase is real. I mean, it does not go to 0 when you go back to the initial value. And something which is very important is that it does not depend on time. Okay, it does not depend. So I will concentrate only on this term here. 0 capital T dt prime phi k of T prime phi dot k of T prime. Okay. Now let's see. I mean, you can just apply. So I will show you the following: that this phase does not depend on T prime. Okay, and this is basically very simple to notice, because basically what you have to do is just to, I mean, the derivative, the time derivative, you can express as the gradient with respect to the R scalar product dr prime. Okay, dr dt. So this, if goes back to something like integral over dr over some circuit of phi k, the gradient of phi k. Okay, so you just change the integral. So you basically, this is just a parametric integral, so you can just express it as an integral over the, in the configuration space, over the, let's say, over the vector here. Just think to a three-dimensional vector. So you use the curl and divergence of as you know. So basically you have to write down what I was saying is that phi dot is just equal to, you apply the composition of derivative of gradient with respect to R of phi scalar product dr dt. Okay, then you have dr dt times dt is just dr. So this goes back to just the integral over dr. Now, what is interesting is that this does not depend on time. So this is an extra phase that the system acquires only due to the path it does in this parameter space. So that's why it's called geometrical. It does not depend on time. It just depends on some path in this parameter space. Let me spend
Sorry,
yes.
go back first.
Yes. Yes.
Yeah, thank you.
Okay. So I just want to give you a picture of this, but I will spend some more time. Okay. So the picture is something I would like to consider okay, so let me do it. I will use a different picture because then it is better. Okay, so let's just give me 1 second. Let's see if I manage to. Okay. Okay, I want to use this picture. Forget about all what is written here, but just imagine the following. Just imagine that you have a state which is prepared here, and then you change the position, and you just do let's say just a closed path on this sphere, but just you assume that the vector is always parallel. Okay. Is this clear, the rule? Hello?
Can you repeat?
Sorry?
Can you repeat?
Yeah.
Yeah, please repeat.
Yes,
Thank you.
I repeat. So let me see. So I want to consider the case in which, so let's say the message I would like to give you is the following. I would like to consider a situation in which, so suppose the parameters, so is it clear that I would like to that you forget about all this number? I'm just using a picture of a nice sphere, okay? So just imagine that the three axes are Rz, Rx, and Ry, my parameters, okay? So this is a magnetic field. So I just start with just something like, so this is nothing. So if this confuses you, so let me, I just draw it, okay? So I want to consider three parameters. Rz, Rx, and Ry, okay? So just imagine that I have a magnetic field that I change in direction, but I don't change in magnitude, okay? So this means that this, let's say, that this magnetic field starts from here, okay? So, and I suppose that I want to do this path. So I just go this way, then I go along the equator, and then I end up in the North Pole. Fine? Okay. Hello?
Yes.
Now, you know that the quantum state is, so now imagine that for the moment, let's forget about the quantum state. I just assign, I have a vector, okay? So I just have a vector in each position, and I want to transport this vector along this path with the rule that the vector cannot change direction, cannot rotate. This is called parallel transport. Look at here what happened. Now, if we do it, then we end up, so I end up with the initial magnetic field, but then the direction of the vector has changed. Do you see this?
Yes.
Yes.
Now, what we are discussing here is something similar. So I change this R along a path. Okay. Now the state will go back to the initial state up to a phase factor. There is some angle. Now, the trick to get such a picture here, which is awful, but I'm not able to draw it nicely. So I'll try once more, but let's see if I manage. I'll try to use some fantasy. So I have this 3 axes, okay? So this is Rz, Rx, and Ry. So I want to change this parameter on a sphere, okay? And this, so and then I take this, like I just take this path like this, and like this, okay? So this is the path I choose. Now, just imagine that the direction, so the state is described by a vector, and during the evolution, the only thing I cannot do is to change, I cannot rotate the vector. Now look what happened here, is that the R go back to the initial value, but the vector forms an angle, theta. And this angle is just related to the sphere, to the type of path. It does not depend on the time. Yes?
There is a question on chat.
Okay, what do you mean by saying direction? Yeah. So what I mean is that this, while moving like this, then the direction, so it's called parallel transport. So I cannot have local rotations. Okay, so during the motion, there is a good picture there. Let's see. So can you connect? Okay. So Valerius found a nice picture. So let's see. Okay, can you see the link that Valerius is proposing? Excellent. Okay. So this is, yeah, you can use this picture. Is this clear what parallel transport means? So I'm not allowed to do things like this. Okay, that it moves and it bends. Okay, it should be parallel. So when I move it here, it should move like this. Okay, then goes up. Okay, so it should not rotate. But then, because of it's moving on a sphere, then basically what happened is that there is an angle difference between the initial and final state. Now, what happened in quantum mechanics, and this was found out by Berry, is that the states, this quantum state, have a kind of parallel transport. I mean, Schrödinger equation has this feature such that if you change adiabatically the parameters of the Hamiltonian, that the state will follow the instantaneous eigenstate, and as a result, the initial and final eigenstate will coincide if the transformation is cyclic, up to a phase. This phase, which is called Berry phase, which is this thing here, does not depend on the time. Okay, this is very important. So actually, sorry, I finish and then I come back to Lien's question. So this does not depend on the time it took. Now I go back to Lien's question. So what do you mean by saying that direction does not change? Okay, so let me explain. So it means the following, that let's see if I, so suppose that basically when the vector changes in time, it does not rotate. So any local rotations are prohibited. Okay, so it cannot happen that here the vector is like this, so it forms an angle. Okay, so it is, so the origin is moved. So just take, I just do it here again. Okay, just imagine that you have this. Okay, these lights. So basically, the vector cannot move. So the vector here should be parallel to the vector there. Should be locally parallel. Okay, it cannot rotate. So when it arrives here, it is like this. It moves here. It is like this. Moves here. It's like this. Okay. Is it better now? Bien. Le.
Professor?
Yeah.
So, actually, the notion of parallel transport is actually, according to my understanding, please correct me if I'm wrong. So, what I understand is parallel transport means that the gradient of the vector relative to the is relatively the same with every point of the path curvature it takes. So
Sorry, I did not hear.
sorry.
I
Yeah.
did not hear you. Can you repeat?
So I think that the parallel transport means that the gradient of the vector that is transported is relatively the same with every point of path curvature it takes. So since the curvature is in the sphere, it should be parallel to every point in the sphere.
No, it means that basically the time, so basically the, let's say the time change of the vector is, so there is no orthogonal component. So while moving, it does not, is not twisting, is not rotating. This is parallel transport. Okay.
So I mean,
So you see that at the end there is a global.
is it isn't it related to the gradient of the the vector gradient?
What gradient?
Because there is I mean since we have a gradient term in the integral, and we have this vector you know on the sphere curvature, so I think it's connected
So
to
let me say the following. So the gradient term is related to the fact that this give you the phase, but this is a result of parallel transport. Is this what you're asking?
sorry, can you repeat?
Yes. Now, what I wrote in the phase in is the result of parallel transport, and then the gradient will give you the phase. Okay. Is this clear or not? No.
I mean, the phase is the result of the integral, or
the phase is the result of the integral, yes.
Or the integrand. I mean,
well, the global phase is just given by the integral. So the local phase is just okay.
Oh,
Okay.
So the parallel transport is just that is such that the vector characterizing the state in an infinitesimal evolution, okay, does not acquire a component which is orthogonal to the vector itself. Okay. Hello?
Yes, yes.
Lienle, is this clear or not? Oh, sorry, I have to read. Can you read? Can you write if it's okay or not? It is an abstract definition, yes. So I try to give you just this picture, so let's try. So let's see the following, okay? Okay, I just tried. So I don't know how to, okay, just imagine the following. So suppose that you have a vector which moves along the equator, okay? This is the equator. Now, parallel transport means that if the initial state, the vector is pointing down, here is pointing down, okay? So you see that basically there is no, I mean, in this delta t, there is no angle. So there is no possibility that the state has twisted. Okay, this is parallel transport. So you just have initial state, then you just do some infinitesimal translation with the vector being parallel to the, after dt, parallel to the previous step. Okay, so that you are not allowing for local rotation. Now, since you're moving on the sphere, then when you go back to the initial, I mean, this is a picture, okay? I'm just using the sphere just to tell you that even if you assume that locally nothing, I mean, you have this condition, then when you do certain path, then you may end up with a state which is rotated, okay? Suppose the following. Suppose that you do this path here, okay? So you just move along the equator and then on some higher parallel. So you do like this, like this, like this, like this. Then you go up and you're here, and then you continue like this, like this, like this, da da da, here, and then you end up with the same state. Okay, so you may have cases in which by playing this this game, you end up with a state which is identical, so which is not rotating with respect to the initial state. But what I wanted to point it out, that there are certain paths. So for instance, if you do the following, so this one, for example, then after a loop, the state is not the initial state, but is rotated. The length is fixed, so the length does not cannot change. What does it mean but split to which coordinates? Oh, I don't understand what does it mean by split to which coordinates. Hello? it lets you project that vector to which coordinates? I'm sorry, I don't understand the question. So why don't we, so I propose the following. Can you write me an extended email and I will answer to everybody, because I don't understand what does it mean you project that vector to which coordinate. So let's do the following.
Maybe she's thinking that the relative coordinate changes because you're using the sphere itself is in Cartesian coordinate, but if you're on the surface of the sphere, maybe it's
what I want to say is, so I try once more, okay? Let's see if I. So suppose I'm on a square, okay, on a flat plane, okay? And these are the value Ry and Rx, okay? And the game is the following. I have a vector. So each point, each point represent a value of the external of the parameter Rx and Ry, okay? Now, suppose that the quantum state is just represented by a vector. So this is the rule. So for a given value of the value of Rx and Ry, I have a vector. Okay. So now what I want to do is I just make a path. So I just change my external parameter in time, in time, okay, along this path, okay. And I'm assuming now, so what I'm trying to use this to explain what happened in practice is that I just transport this, so that the state which is characterized by this vector changes by changing the parameters in such a way that cannot rotate. Okay, so these things is not allowed. So this is not allowed. So this is parallel transported. So this is probably a symbol picture. Okay, in time, in this way. So end up here, and then after a cycle, and ends up there. Is this picture clear?
Yeah, that one is clear, but I think you have another chat.
No, but just a moment. Is this clear? So let's go step by step.
Yes.
Okay. Lien? Okay. So you see that on this two-dimensional line and two-dimensional path, then nothing special happen. If I just allow to move being parallel, then after a cycle, the vector goes back to its initial position and direction. Okay. Now, try to do the same on a sphere. Okay. So I have, so I'm fixing the modulus of R. So the only thing, so I have Rx squared plus Ry squared plus Rz squared equal 1. For simplicity, I'm just deciding that I don't change the, what does it mean? Can you do two-dimension with a curve? Two-dimension with a curve, yes? Okay, let's do two-dimension with a curve. But with a curve is just more messy. So suppose that I have here the state, and I want to move along this curve. Is this the question? Yes, I guess. Okay, so I just move here, move here, move here, move here. I mean, this is like this, okay? Da da da. Then I end up here, 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 and then I end up here. Okay, so nothing changes. Okay, I just transported by not allowing for local rotations. Okay. Now, then since you have to go for lunch, then try the following. Now, instead of considering two-dimensional space, you consider three-dimensional space. And assume that the parameters are fixed. Okay, they don't need to be fixed. I'm simplifying things to move on the sphere just because it's already complicated, and you have the same rule. Okay, so for instance, the vector is pointing in this direction, and just try to do the following. Okay, so if you do move along this line, then here you end up like this. Okay, then you move on the equator, and you see that you move here. Okay, so because we are moving on this surface, then okay, so if you proceed this way, then can happen that when you end up in the North Pole, that there may be an angle. Is this better clear?
To me, it's quite clear.
Okay. So I'm waiting for, so there were two yeses, but from Lien, but I'm not sure this is the final yes or not. Okay, so I propose the following. Okay, so I propose the following. If you wish, so let's try to fix an appointment, say tomorrow or something, because the next two lectures I have to do something. So, and now you have to go for lunch, otherwise it closes. So is it okay that we rediscuss on Tuesday? Or if you want, we can discuss whenever you want. Okay? But I have to tell you about second quantization. So this is important. But I will tell you again about this. Don't worry. Okay, have a nice lunch. Bye-bye.
Bye-bye. Thank you.
There's another chat, Prof.
Oh, maybe after lunch today.
No,
now
I prefer.
I mean, we also have class, no?
Yeah, we have tutorial.
Yeah, tutorial, but at 4. So.
Yeah, I know.
Okay, so I can do it.
Maybe in another day it will be better.
Okay, why don't you send? So, for instance, Monday afternoon after 4 it would be okay for me. Okay, so try to, if it's okay for you, let me know and I will connect. Okay.
Yeah.
Just send me an email saying the only thing I can do it is only after 4. Okay. So we have the lecture, and then we can do it after lunch if you want, or so I'm busy between 2 and 4.
Okay.
Okay, let's do it on Monday.
Okay. Yeah, actually, yes. I think we can find the explanation out there. So I don't know. It's fine.
Whatever. I mean, I'm happy to discuss. Okay.
Yeah. Thank you very much, Professor.
Okay. Bye-bye.
Bye.
We'll go for lunch.